little thing before we have a break. Well, you already saw it, the actual hypothesis test, which is an F test. So, I'm not really going to prove this. We don't really prove things here. This is also the same as mean square for the treatment. If that's the second column, the column in the ANOVA output, you can see it's the sum of squares divided by degrees of freedom. And sometimes we could say like this. The point is, if you think a little bit about it, then the numerator here, which really is the variability between means, and then actually multiplied by the number of observations within groups, you actually know what would the variability of means really be theoretically if they come from the same population. So if the hypothesis is true that all things are with the same mean, I already taught you quite some weeks ago that the variability of repeated means, that's the variance divided by n. It's actually the sampling variability of repeated means. So under the null hypothesis, and then when you multiply by the n, you actually, under the null that nothing is going on, that they are all equal, both the numerator and the denominator, which is a pure measure of within group noise, then they would actually both of them be measuring the within group noise. So this F statistic will be roughly around 1 if nothing is going on. And if something is going on, by that I mean if there is a signal, if there is a group difference of means, if the means are not the same, then it will tend to become larger than 1. So this size here measuring between, you could also say it's also measuring between we never got this one fixed. We tried, but they claim it's okay. We say it's not. They don't care. I want to be the chancellor, so I can tell them they should care. If nothing is going on, it should be around 1. And then some theory, mathematical theory, statistical theory, tells us how would this behave from sample to sample, or rather from repeated 3 samples to 3 samples to 3 samples. How would such a measure actually behave? Well, it behaves like an F distribution. Did we meet the F distribution before in this course? What's that? No, I think you're right actually, because I really meet many distributions all the time, every day in all courses and in all endeavors. So I was slightly in doubt for a second whether you actually met this, but I think you're right, we didn't meet it before in our course. So, hey, what's the big deal? Another distribution? We thought we were at the end. Do we need more distributions? Well, yes, you do, goddammit. You need many new distributions in life, but now we don't get too worried about meeting new distributions because it's just a distribution. Hell, it has another name. I don't care about names. It's just a distribution, so let me hear it, let me meet it, and I can deal with it. There are many different F distributions around. The F distribution, theoretically, comes as a consequence of taking 2 chi-square distributions and dividing them with each other. So that would be the mathematical way to derive at the F, to take 2 chi-squares, and then you need a transformation rule from a probability course to how to find the distribution of the proportion between 2 things. I only told you how to simulate it, that's fine. But theoretically, you could also find it, and you would find that if you take normals, then you square normals, you get chi-squares. Then you take 2 chi-squares, divide by each other, you get what is known as the Sneedy-Course F distribution. It's just a distribution. We need to know the number of groups and the number of observations to know exactly which F distribution that would be the right one. We talk about numerator degree of freedom and denominator degrees of freedom. So that would be number of groups minus 1, and then number of observations minus number of groups. These are the two numbers which are also given by the software in the ANOVA table. That is because these are the important numbers to find the right F distribution to use to do the hypothesis test. And so we would just go ahead, compute the F, and find a p-value as we've been taught a few times. For constructional reasons, the way we find the p-value is like this, and we don't multiply by 2 or anything, because the construction in itself is in a way non-directional, so both small and large deviations will appear like that. So the F distribution is just another skew distribution on the positive axis. F statistics can only be positive. And here's an example of an F distribution. I've plotted in the observed F in this case. And to find a p-value, we find the probability of being to the right side of this. That would be the p-value when we do F testing like this. So this is the test statistic. This is a copy of the slide I already showed you, but here it goes again. Now I told you a bit of the theory about why this is a good measure, because when there is a signal, the MS treatment tends to grow, and then we use it's kind of a signal to noise ratio also, if you like that terminology. It's the signal divided by the noise, and then since the signal also includes the noise actually by theory, then if there is no signal, it's this noise divided by noise, on average 1, and it distributes like an F. And only if we have an F, a signal to noise, which is extreme in this proper F distribution, we can reject the hypothesis, we have a signal, and we can prove that groups are different. This is exactly the result that R is telling us as default. Sum of squares, mean square, the F, which is just these two divided by each other, and then they look up the p-value in the right F distribution for us, and they have the usual star notation. We are below 1 per mil, so pretty strong evidence against the 3 groups being the same, which, by the way, would have been what we would have put our money on by looking at the data in the first place, because they look pretty different, these toy data, in the first place. So I think that all makes sense. And I think this is a good place to do. I'm a bit over time, but that's not the problem. Let's see. TV data. Come on. Yeah, there we are. Not too bad, actually. I created a situation with a very small p-value, just as we just saw in the other example. The small p-value, these are the Bang & Olufsen data, so there are 12 groups in this case. They are all actually only evaluated twice in this case, so there are many small groups of data. Because this is the data from just one person. I will zoom in on a very small part of the data for just one of those evaluators in the game here. So yes, they are different. And I express it in 2 similar ways. So that's what we should learn. We have clearly significant results. Fertilizers on the top. So let's break it and be back in 15 minutes from now. 5 after, I'll begin again.